I'd like to thank the organizers of the conference and Carolyn for risking their reputation and letting me speak today. I do apologize in advance for the black slides that are a little harder to see, but I am a millennial, so black is cool to me. So I do apologize for that. The demonstration of some of the stuff down the line will be on a nice white background. So first, can I cold open with a joke? I heard that that's a good thing to do. This is special for my son, who's turning 8 years old. So when does a joke become a dad joke? When it's apparent. That got the appropriate amount of chuckles, probably all of you parents. It got me thinking, actually, since I'm an engineer and I overthink most things, I originally assumed that when I became a dad, that the more kids I had, the funnier my dad jokes would be, right? It's multiplicative in some sense. But I actually realized the more kids I have 4, that it actually follows the equation e to the negative x. Whereas the more children that you have, it is a drastically decreasing funniness. So again, if I attempt to throw any jokes in here, you could give me a courtesy laugh if you want to. You don't have to, but I just thought that was funny. So quick outline, a little bit about me. What is computational design? I think it's good to address that because there's a lot of definitions that have been floating around. So at least from my perspective, I'd like to talk about what I think about that. And then we're going to go a little bit into the anatomical reasons why we even do this thing in the first place, go through a history of additive and orthopedic devices, and then discuss why computational modeling. Why use this as a resource versus traditional CAD? Why does it go hand in hand with 3D printing? And then we're going to go through a couple case studies. I am a daredevil, so these are going to be essentially live demonstrations. I would like to leave enough time for questions. I've got my eye on the clock for that. So first, a little bit about me. My wife and I have 4 kids, plus one on the way due in August. We're a very musical family. I think a lot of the times engineering goes hand in hand with people who are also very musically expressive. So my wife and I have both been playing the piano ever since we were 4 or 5 years old. I like to say that my house is akin to living in a real life musical because all of my children are singing at one point or the other, and you never quite know what it's going to be. I love coffee. So if any of you have a chance to talk to me afterwards and you're also a lover of coffee, not only do I roast my own beans, but I also have just about every brewing method of coffee that I think is out there, except for Turkish coffee. I still need to acquire that stuff there, but I love coffee. And then, I've spent the last handful of years working in the orthopedic space, specifically on the biomimetic aspect. So it's how we use and leverage computational tools that are available to us nowadays to be able to take things that we find in nature and adapt those for human use products. So not necessarily just in the orthopedic space, but I also have actively worked in projects that are in consumer goods, wearables, filtration systems for sand filtration as well as heat transfer systems. And then there's just a few of the companies somebody once told me that recently it feels like I'm collecting companies like somebody collects rocks. So just a few companies that I'm involved in. A lot of these are, some of them at least are initiatives for public education. So like Lattice Robot, give it a Google. It's basically just a catalog for people that don't know about lattices to learn about lattices, and sort of a fun free project that me and a couple other people were working on. What is computational design? Let's go through some things that it's not. Computational design is not computer-aided design. I had somebody cheekily come up to me and be like, well, AutoCAD is using a computer to design stuff, and they've been around since blah, blah, blah. But for the purposes of this conversation, contextually, computational design is not computer-aided design. Computer-aided design is using computer to be able to assist with the design process, but not quite what we're talking about here. Computational design is not parametric design. The vast majority of engineers in the space are very familiar, I think, at this point with parametric design. So just as an example, we've got a profile, let's say a lateral profile of a cage mimic, and we have general design principles of the cage, maybe a lordosis, maybe certain design features, instrumentation, and whatnot. But we have the height of the cage changes, the depth of the cage, the width of the cage. So we assign parameters to those values. We build out a design table that allow us to essentially create 30 or 80 or 120 SKUs all with one sort of design tree. But computational design is not that. what computational design is algorithmic design. How many of you are familiar with the term algorithm? Okay, most of you. My first exposure to the term, my father is a professor of computer science. He's been doing that for 35, 40 years. And I first saw the term on a textbook that he had brought home when he was preparing one of his lessons plans. And I asked him about it. We got into a discussion, and that's when I realized I was too dumb to be a computer scientist. But essentially what an algorithm is it's just a series or a list of execution steps to be able to accomplish something. What computation design is a systems design process. So it's a field that involves the use of computer algorithms, simulations, and data analysis to support or enhance the design process. How this differs from parametric design we'll get into a little bit down the line. It incorporates a lot of parametric design principles. Most of the workflows that I build for customers include some sort of variables where they can adjust parameters. But the way it goes about those steps is a little bit more computationally intensive. It may include simulations. It may include other calculations outside of what the engineer can directly control through data input. I'm going to try to give an example. So I was thinking about this just the other day as I was mowing my lawn. We got a pad that we poured. We're going to put a shed there. I don't have a zero-turn mower. I've got a lawn tractor. It's better than a push mower. But I realized that I couldn't quite mow the square perfectly, right? Because I can't turn my zero-turn mower in a way that lets me cut perfectly to the corner, turn, and cut over to the next corner. So I got to think about like what algorithm or series of steps would I write in order to be able to go and mow this thing most efficiently. And so the first thing I started thinking about, well, I could go straight, cut, take a U-turn, cut down the other line, and then do that essentially in a 90. What that leaves is essentially these semicircles of space for cutting. As you sort of enhance or grow those semicircles, eventually you morph into the circular pattern or oblong pattern, since the patio is longer in one direction. So I'd like to take this to 3 dimensions just to show you something that I'd like to sort of chat about. If we can get there. So does anybody know what would happen if we added a sphere to a cube? That's a little bit of a rhetorical question. And some of you that are used to more traditional CAD might be raising your eyebrows and being like, that doesn't really make any sense. How does a sphere get added to a cube? Well, I'll show you. In the realm of computational design, that's totally possible because we work with things like fields. So we've got a sphere, we've got a cube, and this is a sphere cube. So basically, it is the addition of a sphere and a cube. So what I think is fascinating about computational design is the fact that we use algorithms or a series of steps to be able to produce end-stage designs. A lot of the times, lattices, complicated structures, surface roughness are things that we encode with an algorithm that we couldn't possibly create by hand. These are extraordinarily complicated things. However, the downside to these is that it introduces a level of ambiguity into the design that the human doesn't have control of anymore. The engineer can assign and create algorithms, they can have feedback through various systems, but in order for them to be able to have full control at the level that a med device requires, there ends up being some ambiguity. So let's say we multiply the sphere. We're going to multiply the sphere by a factor. Let's just call it 0.5 for now. We'll assign that to a variable. And then what we're going to do is do a subtraction step, and we're going to subtract 1, basically our factor from 1. And then we're going to do another multiplication step, and we're going to multiply our other object, the cube, by the remainder of that, and then we'll add those together. So what you'll be able to see is essentially, I've not clamped this, so I'll try to be careful. But as I set this down to 0, it's a cube, and as I set this to 1, it's a sphere. Well, actually, I was hoping to do a drag and drop, but we won't clamp it. Actually, I could probably do this right here. All right. So now we can only go from 0 to 1. So what you'll notice here when I drag between the two is we go from sphere to cube, right? If I set it at exactly 0.5, one would argue that there is equal parts sphere and equal parts cube. But in the general sense, using subjectivity here, I'm going to get a different answer if I set it at 0.4, 0.5, 0.6. Some people may still say, hey, this still looks like a cube, and we're down closer to a sphere. So this idea that I want to drive home represents, in my opinion, a fundamental problem of the idea about computational design, which we must rectify. And it's the fact that these algorithms oftentimes are so complicated that we wrestle with how we properly define them in a regulated industry. So I would like to use this idea about the sphere cube as our nice representation. So, cube sphere. We'll call them cube sphere, or sphere cube. It depends. Whatever you want. So how many of you guys are familiar with the idea about requirements not being ambiguous and not being conflicting, right? When we define requirements, what we need from them is that they don't conflict with each other so that all of them can be satisfied and that they're not ambiguous and they're too open to subjectivity. So this idea about cube sphere, in my opinion, I really love it because it's like, is it a cube or is it a sphere? Well, it's both, but a lot of the times in our black and white worlds, we need to force it into a box, pun intended. So I want to revisit this down the line as we start talking about the complexity of algorithms. But first, we're going to pivot to, I think, what a lot of you will be familiar with, and that is this idea about why we need computational design in the first place. Most people are familiar with Julius Wolff's law. Basically, it's this idea that bone adapts to its local environment through some sort of mechanical loading. There's a certain amount of loading which bone likes to see. It grows. When the bone doesn't see that load, it resorbs. When it does see the load, it adds to itself. Less people are familiar with the work of Harold Frost and the Frost mechanistat theory, which basically further expounds upon this general idea. And it's that there is a mechanism by which this stress and strain is monitored, and therefore relates that to what happens in the biology of bone. And the modeling adapts to certain types of overloads, and it will, again, remodel where it needs to. It'll take away where it needs to. Recent literature, I think actually a paper published in 2023, has affirmed this mechanistat theory, and researchers are still arguing about the nuances of exactly what happens, but most people are aware of the fact that certain rates of strain are better. This is one of my favorite graphs. I actually, I love talking about it. I love looking at this idea, because when we design implants, they are surrogates, right? What they intend to do is replace a portion of the body. But most of the time they do so poorly, at least in terms of a biological aspect. They don't operate as well as what used to be there. I apologize, I'm gonna get my phone out because I'm prone to babbling. And I wanna check the time. So this idea that we have a overload zone where the bone actually starts to remodel itself, most people are familiar with. When we design an implant that replaces that, and we use a material that's not bone, in vast majority of cases, there's a stiffness mismatch. The other thing that a lot of people probably realize if you told them, but don't necessarily when they're designing it, is the fact that we're designing static things to go into a living system. Bone, if we're trying to truly mimic bone, the trabecular nature of bone has the ability to resorb itself and where it sees a fracture, right? If it sees loading in a certain spot and not loading in a certain spot and it fractures, it's going to resorb itself to make use of those materials somewhere else. That's not available, at least not in the current technology with computationally designed products. So we need to be a little bit careful, in my opinion, when we design these surrogates, that we don't necessarily just say, hey, this looks like trabecular bone. Well, great, it's titanium. So what's the point? Let's measure the output. To further expound on this, again, study after study have sort of confirmed that it's so very important to understand what happens to the body at the macro, micro, and nano level. And again, this stuff has been pounded into most people's heads that have been in the industry. So this idea that cyclic loading of bone as less than 1% of the ultimate strain can cause measurable differences. So we're not even talking about a ton of load. We're talking about this idea about microstrain and microstrain's ability to remodel. So when we have any material that's a modulus mismatch, and I don't care if it's PEEK, I don't care if it's titanium, I don't care if it's some other type of surrogate, even an allograft, any mismatch in the local native bone, because remember, again, bone is not a static material modulus. It changes over it in time and space. So this idea that the stiffness of the thing that goes in it has a profound effect on this kind of stress shielding. And so why is it important? Again, why is computational design and additive manufacturing important? Why have we seen an explosion in the growth of it? It's because of this idea about reducing stiffness. Reducing stiffness and integration into the local anatomy. So the early 2000s saw the rise of PEEK. And again, most of you guys are familiar with that. I was talking to some of the other today, and I think PEEK sort of had its heyday in the late, mid 2010s, where it represented the vast majority of implants in the spine space that were going into the bodies. The stiffness reduction was great over titanium as a raw material, and although it was biocompatible, after a few years of usage, people were starting to realize that it lacked the osteogenic capabilities of titanium. So whereas titanium is a generally osteogenic material that bone likes to attach to, it likes to integrate to, PEEK was not that. So although there were certain technologies, spray technologies that had been added, different coating technologies, it sort of fell out of favor a little bit, and we started to see the rise of titanium again. The additive orthopedic industry, in my opinion, it's fascinating because we went from early investigative stuff, things that were a little bit more like 3D printing for medical modeling. The very first sort of patient-specific guide was done, I think, by Anatomics. And so you can see here just, again, a little bit of the step through where we got like some of the first cages, and then in 2015 the Stryker Tritanium came out, the PLIF 510K, and then on and on and on. And so we've gone from an explosion in the submissions. So if you just look at papers on orthopedics and 3D printing from 1999 to 2015, you can see the exponential rise. It started to take off in a huge way. But by 2014, again, my opinion, the metal AM technology, what you could build, the designs you could realize started to outpace what could be created. How many are engineers in the crowd? So a good handful. How many of you guys have ever tried to design a complicated structure using parametric CAD? Like in SolidWorks, let's say. I want to design a series of lattices I'm going to cut or pattern. There eventually becomes a problem with that. Now again, I'm not going to give a spiel on a particular type of additive software or the other, but I will say that parametric boundary representation design struggles a lot with complex structures because you're using points, vertices, lines to try to, and surfaces in space to represent what could amount to hundreds of thousands or millions of surfaces in some cases. So there was essentially this new technology with this like crazy amount of ability to be able to recognize these new structures, but the design tools remain largely parametric. Early softwares, Grasshopper, which is largely used outside of the med device community, within medical, which a lot of early stage AM and orthopedic device adopters got onto, and then NTOP Element, basic latticing, limited tool sets, hindered by interoperability. One of the sort of flagship products that brought computational design, in my opinion, again, into the engineering mainstream was NTOP Platform, which is now just called NTOP. So it used a kernel called implicit modeling, which is basically mathematical representation of the structures, as well as what's called sign distance fields, which again, I'm not going to bore you with the details, just it's a different way to represent objects in space, makes things like complicated lattices and surface roughness possible. How many of you guys know who this is? So this is Dr. Ulf Fernstrom. How many of you guys have heard of the Fernstrom ball? That's actually really surprising. So this was one of the very first motion preservation devices. Prior to his invention, which is literally just from the Swiss stainless steel ball manufacturer, or ball bearing, it was a ball bearing. I believe that the first attempts at this were actually using cobalt chrome. And so what I want to show is basically like, if you look at anybody's product portfolio nowadays is using 3D printing, it's really complicated, right? But we've come a long way in the last 80 years or so since this first idea about motion preservation was to implant a ball bearing in somebody's spine. So again, initial limitations I'm showing here, again, no knock on anybody's products if you see them here, from what was considered, again, pretty state-of-the-art back in the 2010s. Again, fairly basic geometries. The lattices all use the exact same algorithm called a Voronoi, if they did even have sort of a technology. And you had some basic surface roughness. Now you have the ability to utilize this field-based design to create designs which would have been unthinkable even 5 or 10 years ago. Just some really cool stuff. So I apologize for the wordiness. I'm going to try to summarize this. But this sort of is talking about some of the limitations that are regulatory in nature. I by no means am a regulatory expert, but I have beat my head against the FDA wall on plenty of products over and over again. So I have a pretty good understanding of the framework of this kind of a problem. Most people are familiar, again, I'm going to use interbody devices as an example, with the fact that, hey, you got to pass some testing to get to the FDA. Most people, I don't think, realize the difference between the FDA-required testing and an anatomically relevant loading condition. So the equivalence idea is basically any devices that were legally marketed prior to May 28, 1976 were sort of considered in, right? They were good to go. There was enough history in the field for them saying good enough. Everything that's been cleared prior to that must be equivalent to that. So there's been a chain of devices that you can basically claim equivalence on, but all of them lead back to essentially this FDA Act in 1976. Here's, in my opinion, the problem right here. This idea about what is a anatomically relevant loading condition, what you can throw in there as an implant, which should be good enough, and then what we're required as a bar by the FDA. And the fact is that even by conservative estimations, the numbers are off by about 10 to 25 times in most loading scenarios. And why is that? Well, most of the devices that we're basically comparing ourselves to were already too strong. They were just hunks of metal. So as we start to look at the computational design, we can lower the stiffness, we can match the modulus of bone. Less of that matters, in my opinion, if we also don't see some kind of a change in the regulatory nature of the products and how they're being regulated. Some people have managed to get as low a stiffness devices, I think, as possible, but eventually they'll run into the same problem, which is just the device is not strong enough, it doesn't last long enough in cyclical testing. So one of the ways that we can try to do this is carefully balance strength and flexibility. Strong enough as much as it needs to while being as flexible as possible, which is a really hard problem because if you're familiar with a modulus of elasticity, it usually looks like the thing on the left in its linear elastic range, which again, we don't want any of our products to plastically deform, so we're there. High stiffness is correlated with device failure and subsidence. Insufficient strength is going to cause devices to break, and obviously nobody wants that. So an appropriate range will reduce the implant's biological footprint. I say that in parentheses because it's just a term I like to use. I don't know if I coined it or if somebody else did it before, but I like to say the best implant is one that's forgotten by the body. Right? Eventually, I think we're going to move towards additive biologics that can resorb out of the body and leave nothing but natural bone. Again, we're not quite there. So I'd like to think the thing on the right is more ideal, where we can kind of maintain stiffness. There's a key zone here as strength increases, but we don't increase stiffness equivalent to the strength, which again, hard problem to solve. Old design, 22,000 newtons is the load. That's a 50th percentile compressive force of 510K submitted devices reviewed by the FDA. 500 newtons is a clinically relevant lumbar intervertebral load. So that's 40 times difference. And again, I'm an advocate for additive devices. I'm an advocate for computational design. So of course I'm going to frame the problem as like, this is ridiculous. Is it necessarily that bad? Probably not. Obviously this is a little bit of, for the presentation. But the fact is there's a wide gap in what the body sees forces-wise on a day-to-day basis and what we design products for. So the other thing is, again, no two anatomies are the same. Duh. The geometry is not the same. The loading conditions are not the same. People are different sizes and shapes. Their body is different sizes and shapes. So when we think about a parameterized design, even if we fill that parameterized design with as small as steps as possible, heights, widths, lordoses, we still don't necessarily get a match, any at all. There's never an anatomical match. So computational design is something that we can use to basically be able to do that. So what's the solution? Computational modeling just allows for the creation of ordered and random structures to decrease stiffness. It allows us to grade those structures, density, and morphology in order to be able to adapt to various loading conditions. The FEA portion allows us to basically use FEA, which is essentially modeling of those structures digitally, as a feedback loop back into the parts themselves to be able to inform the design process. Again, either as you're doing your iterative development or as part of the patient-specific process. And then the computational modeling allows us to compute massive data sets. So again, most of you guys probably are fairly smart. I like to consider myself fairly smart, but there's not one human that can process a table that's 100 by 100 very quickly, less 1,000 by 1,000 or 10,000 by 10,000. But essentially, that's what these things can do is they can use analytics, statistics to basically process massive data sets that are able to inform the designs. Just a quick idea again. A gyroid structure, some of you guys are familiar with triply periodic minimal surfaces, TPMSs. The ways that we can manipulate that, 6 ways, look entirely different, but we can shape, grade it, we can remap it, we can grade its thickness, we can grade its cell size, and we can also create, what I would consider more true bone surrogates than what's currently available in a lot of those cases. A quick idea about this idea about intentional structure design. So stochastic lattice, I would say, again, cursory review, probably exists in close to 50% of cages that are out there on the market. A lot of people call it stochastic. Some people call it by its name, which is the Voronoi algorithm. I get a little triggered when I hear it called trabecular, because it's not trabecular bone. Again, personal opinion there. What we're doing is we're just comparing it to two things that occupy the exact same volume fraction. So when we compare the stiffness of structures, we like to be able to have a level playing ground, right? So it's the exact same volume of structure occupying the space. So perforated TPMS structure, again, exact same volume, 18% reduction in stiffness. If we remap and essentially we take the structure and we sort of morph it in space a little bit, we can now achieve a 45% reduction in vertical stiffness. Again, exact same representation of volume. If we take that design even further, now again, we're going to also want to balance, well, all right, great, Matt, the structure is flexible. Who cares? Does it actually hold up to the loading? So by making slight changes, functionally grading the material of the device away from areas that see no stress and into areas that do see stress, we're able to drop the volume further and then increase the stiffness to 61%. So in this case, you can see we dropped the volume 476 to 276. And what we did is we moved material into places where it needed to be and took material away from places that it did not need to be. So here's a quick cross-section showing the difference between the two. It's really, really small. Most people would be surprised at how small amount of materials needs to move from A to B in order to fundamentally change the stiffness and or other properties of a structure. But again, with the computational modeling aspects, we are able to achieve these with a high degree of accuracy and be able to, again, do things that were previously not thought possible. I'm part of an initiative, a project called Lattice Robot. So what we're attempting to do is categorize all the lattices that are out there. Every single permutation of lattice, every single functional permutation within that lattice, cell size, shape, grading, things like that. Most of you guys are familiar that there's a material library, right? And properties of material, I mean, how many people haven't Googled, like, what's the properties of titanium? I do it, like, every other day, because I can't remember that. Now you talk about this use of metamaterials, lattices, and the fact is that they're multiplicative. You've got base substrates that you want to melt parts out of in 3D printing, and now you have all of these available lattices to you. So again, within one lattice family, TPMS, let's say, there are something like 75 known triply periodic minimal structures that have been modeled. And inside each one of those structures, you can do, again, change the cell size, you can change the thickness, you can adapt and grade it in various ways. And so now, again, you've got access to tens of thousands or hundreds of thousands of unique variations or permutations of structure. And so the fact is, again, if I asked you to find the red line, how many of you guys are going to spot it? It's kind of hard to do. As we step through the slides, you can see that we've made the red line darker. So a lot of the times these computational design tools are to help us better inform the type of structure or the design that we're doing. Is it going to pick the right structure 100% of the time? Probably not. I mean, there's still a huge amount of engineering involvement that needs to be in these design tools, but this idea that it allows us to leverage this kind of a thing, I think, is important. So I'd like to just pop to and show a couple things real quick. Live demos, so to speak. So the first one we're going to look at is this idea about patient-specific. Most people are familiar with patient-specific, the general idea, and the fact that we can create conformal geometry. So in this case, we've got a nice conformal implant. I just want to show you how quickly you can essentially adapt an implant in the space. So this is an implant that's perfectly conformal to the top and the bottom. We've gotten some target widths, depths, various height metrics, as well as pitch. I'm going to highlight essentially the trajectory that the implant's essentially going to be inserted at. And we're going to move the target to a different segment. So the target in the different segment, we'll notice here, hey, I didn't quite place it right. That's okay. I'm going to go ahead and scoot it back a little bit. I'm going to decrease the target depth to something that's more anatomically relevant for that segment. And then I notice that my pitch is a little bit high for my targeting, so I'm going to set that to 0 and now pitch the implant. What I think is incredibly cool is the fact that it doesn't have to be a one-size-fits-all. So in some cases you say, all right, conformal geometry, cool. There are people that are doing that. Carlsmed comes to mind, of the ability to match the bony segments on the top and the bottom vertebral bodies. But there are a lot of cases that's not necessarily the ideal scenario. Maybe I want to do a rasp of the space, and that way I can confirm that my end plate to end plate is going to be a nice amount. So in that case, that's fine. We can essentially create cut geometry that can operate the same way. So the cut geometry can essentially take our target, and it can create a cut path, right? A surrogate cut path, and it can size the implant appropriately for this space. So again, simple example, but you can see that the idea behind taking a patient scan in, being able to set a target point within a workflow, instantly get something that conforms to the anatomy, and then set up another key couple of rules to be able to create things incredibly fast. So this is, in my opinion, one of the huge advantages of computational modeling. Whereas before, having to take each individual piece in, put it in the right spot, segment it, do some sort of a subtraction operation to get it in the space, is something that would be a lot harder to be able to execute on. The second thing that I would like to be able to chat about is this idea of adaptive stresses. And most people have started to pick up on the idea of computational modeling can be combined with FEA and various solvers to be able to further augment what we're capable of. So this is just a simple example. I'll actually be further expounding on this at the Computational Design for Additive Manufacturing Symposium, which I think is sometime in October. And this idea about adaptive stress structures. So we've got a first structure. We're going to load it with a force. We'll look at that initial analysis. You can see here, nice and springy, basically the force. And this idea that we've got a particular vector, and what we're going to do is we're going to use that vector field and the stresses to define what happens to the structure. So we can essentially remove areas of the beams. We can adapt areas of the beams that are seeing higher versus the stress than others. So the first is, all right, we've got this piece right here. What happens if I load it again? Because I see this a lot in a lot of people I talk to. Most people see stress in an area on a lattice and they say, well, just put more material there. The thing is, the stress moves around. It's going to move to a different spot that's weaker. So in our second iteration, when we go ahead and run that, right, say, okay, well, we solved the problem. We put material where it was stressed. When we look at this analysis, what we see is that we're still seeing areas of high stress. In some cases, it's at fringe or border cases. In some cases, it moves. If we attempt to re-thicken other areas like that and use the new stress field as our new target, then again, what happens when we test it? Well, now we've perpetuated the problem back to areas that the stress wanted to go through first in the first place. When we use computational design, we can essentially inform as an iterative loop what happened the last time, so we can continue to adapt. So in this third iteration, it's basically, all right, well, remember 1, remember 2, now create a third structure that's based upon both 1 and 2. When we create an analysis of that, the analysis is perfect. Everything is under the yield point. And what, again, I think is incredibly fun to illustrate is if I decide that this particular orientation or the loading wasn't exactly what I needed, then I'm just going to change the load. And I'll talk a little bit. So computational modeling in a lot of cases is really, really fast. What used to take a long, long time, meshing algorithms, performing simulations, now can be done at a fraction of the time. There are certain meshless simulation procedures which allow us to take implicit level geometry, perform those series of calculations to be able to get to what our final iterative solve is. And again, if any of you that are familiar with really deep into the FEA know that this kind of a thing has evolved incredibly rapidly in the last even just several years with the techniques that are available to us. So as I kind of close out, the demo portion, again, simple examples. I didn't necessarily want to go hyper deep into specific applications. But this idea, again, that we can take, parts themselves, we can load them, put them into the space. And again, what you've seen here is that I've just changed the orientation of the structure. So instead of it being, negative in a certain direction, it's now positive. And now we've completely changed the look of the structure through adaptive, informative, iterative loop in our process. So again, one of the super powerful things that we have. The last thing I wanted to go over is, kind of this idea like, hey, we're doing a lot of traditional design. We started getting into 3D printing. We've got a handful of designs. What should we do next? And the learning curve in a lot of these softwares is pretty steep. In some cases, it's a little more general. But if you're wanting to design something that's truly cutting edge, it's like, what do I do? Well, again, first I would recommend get a good fundamental understanding of what a lattice is. What do these structures do? What can I use them for? The domain knowledge is incredibly deep because we've only talked about a lot of structural problems. Once you incorporate the biological aspects, right, the pore size, the roughness at both the macro and micro level, our ability to use surface texturing as implicit fields to create these novel surfaces, it gets pretty deep. So the first is understanding, again, what does bone need? What does it want? The cool thing is there have been hundreds of papers in the last 5 or 6 years specifically on additive in the orthopedic space. A lot of people are interested in it. So I would say that's a perfect aspect of something to do. The next is, don't necessarily hesitate to invest in the tools of today. Most people are like, I got traditional CAD, I'm already paying for it, why do I need another software? And the fact is that, again, in my opinion, I think a lot of these softwares will stay pretty parallel to some of the traditional parametric CAD tools. Those aren't going to go away, but not having them in your portfolio from a development standpoint, as we start to see the world of lattice explode. Again, I'm an advocate, I'm kind of an evangelist for this idea about lattices, but not just me, but there's a lot of other industries that are prime for the metamaterial space. Lattice being fairly colloquial term, but this idea about metamaterials in the space. So metamaterials, again, now structural, also biological, heat transfer, vibrations, optical. There's a lot of different ways that these things can be applied. And looks like I got about 5 minutes left. I'd like to leave some opportunity for questions. Again, really appreciate the opportunity to be able to come and speak. And I don't know if they have a mic. Oh, perfect. I don't bite. Ask a question. I think it'll be good for just the general a flow of thing for people to be able to know. Again, if there's no questions, great. I will take my leave. Oh, we got one. This peer pressure.
So what do you think about the interoperability of implicit models? Because I think that is one of the big problems with NTOP. Like, what do you do with it after you've done your cool mesh?
Exactly. Yeah, no, you hit on a good point. And I am not an NTOP advocate. They don't pay me anything, but they've really been pushing this idea about implicit format. And I think they had a slogan like 5 years ago, like death to STL. And again, most people that are working with extraordinarily complicated things have probably wrestled with a mesh or two. Something that hits 250 megabytes, 400, 500 megabytes. I mean, personally, I've worked with 1 to 2 gigabyte files before, and it's like, what do I do with this? So this idea about implicit representation only works if you go directly into your machine format, like slice, let's say. Again, NTOP and others are trying to push this idea about implicit representation in order to make everybody's lives easier to not have to go mesh. The 3MF consortium is a really big pushing into this. So they're trying to get as many software companies, machine manufacturers on board to be able to use 3MF. Now, right now, 3MF is not as lightweight as implicit, but 3MF is currently working on an implicit representation to be able to interoperate between. And I believe that they, if anybody's going to go to Rapid 3D Printing Conference in LA in a couple weeks, the 3MF will be having sort of a discussion about several key players that have just been added to the 3MF portfolio for helping with that. Because again, you can design the coolest things in the world, but if you can't figure out how to get them to a printer, then what's the point? So good question. Anybody else? All right, looks like we're done. Thank you very much.